Hello everyone and welcome to Engineer Tomorrow's 14th video in the Thermodynamics video series. Today the subject that we will be discussing is the ideal gas equation of state. And the reason we're going to be discussing this equation is because oftentimes, the information in the back of the books, the thermo books, are very helpful, but we want to be able to do our calculations quickly, efficiently, and sometimes you don't have the tables in the back of the book, from the back of the book in your exam, or you're out in the field trying to do a quick calculation, you don't know what those values are. So it's convenient to have an analytical relationship that you can use to determine values such as the volume or the pressure or the temperature of a gas given other conditions. Okay, so first of all, I want to address what I'm talking about when I say a gas, an ideal gas, okay? So if I draw the pressure versus specific volume plot of the water vapor dome, or not water, sorry, liquid vapor dome, okay, we see that the liquid vapor dome looks like this. And if you don't understand what this is, I encourage you to look at our previous videos. But essentially, what you have over here on the left-hand side is you have a liquid, and you have a liquid vapor mixture, and then if you get to this side, you have the vapor. Okay, but as it turns out, as you increase your distance from this liquid vapor dome towards over here in this area, okay, you start getting the vapor starts behaving like an ideal gas. Okay, so when I say ideal gas, it has to be in this superheated region in order for this equation to be applied. And there's ways to calculate to see, how close is your condition. Okay, so maybe you're over here. So how close is that to the ideal gas assumption? And I believe we'll be discussing that in the next video. But just so you know, this is what I'm talking about. We're in the superheated region, and something you can think about is air. Okay, so this could be air, where the boiling point of air is at a much lower temperature or much lower pressure. So we're in this region. Okay, so just to give you some quick history, some of you might be interested. In 1662, Boyle discovered that the pressure is inversely proportional to the volume. So as your pressure increases, your volume has to decrease for constant temperature. Okay. Additionally, in 1802, a scientist by the name of, his last name is Charles, he discovered that for very low pressures, so P low, okay, he discovered that the volume was directly proportional to the temperature. So as your volume increases, maintaining a constant pressure, your temperature increases as well. So, using these two relationships, they determine a combination of the two relationships, which also accounted for the mass, or the quantity of a substance of a pure substance that you may have, and that relationship combines to become the ideal gas law. So let me write that down. Ideal gas equation of state is what it's generally called. Okay, and that is essentially the pressure times the volume is equal to the number of moles, which we are not discussing in this series, but I encourage you to look it up if you do not understand what it is, times the ideal gas constant. I'm going to put a bar over it, and I'll explain that really soon, times the temperature. Okay, so as you can see, as your pressure increases, your volume has to decrease so that you maintain the same number over here for a constant temperature, assuming that the quantity that you have remains the same and your ideal gas constant doesn't change, which it doesn't, as long as you have the same substance. Okay, so So it turns out that there's a lot of different ways that this equation can be written as well. So first of all, this ideal gas constant, so R bar. This is also known as the universal R, and in thermodynamics books sometimes they just list off R, but R is a different value than R bar. So R bar, we're going to say, is 8.314 kilojoules per kilomole Kelvin. Okay? And, you can also write this as 8,314 joules per kilomole Kelvin. Okay, and the way that you can find R is you use, first of all, let me show you how the equation looks with R. So with R, what you get is the pressure times the volume is equal to the mass times the R constant, which this R is specific to whatever gas you're actually using. And the relationship is found using the molecular weight of the substance. And this is multiplied by T. Okay, so how did we get from this point up here to this point over here? Okay, and the way we actually did this was using the relationship that the mass in kilograms is equal to the number of moles, okay, kilomoles, times the molecular weight of the substance. And the molecular weight is in kilograms per kilomole. Okay, so if we look at this relationship up here and we want to substitute, our mass, what we have to do is we get our pressure times the volume equals, so just solving for N in kilomoles, we get the mass divided by the molecular weight. So mass over molecular weight, okay, times R bar times T. Okay, so how does this relate to this value up here? Well, you have your pressure, your volume, pressure, volume, mass, mass, temperature, temperature. So this R bar divided by the molecular weight. Need some more space. R bar over molecular weight is equal to the R value that I'm talking about. Okay, and that would be in kilojoules per kilogram Kelvin, and this is kilograms of whatever substance you actually have. Okay, so it's important to really know that which ideal gas constant you're using. Is it gas specific, or is it just the ideal gas constant? Additionally, I wanted to show you guys some other forms of this relationship as well. Let me get my pen back. You have, I already said this is pressure times volume is equal to the number of moles times the ideal gas constant times the temperature. Okay, or you can write down pressure times the volume equals a mass times R bar over molecular weight times the temperature. Or, sometimes you encounter the pressure equals mass divided by volume is the density times R bar over the molecular weight times the temperature. Or you can also find it as the inverse of the density, so pressure times the specific volume is equal to R bar over the molecular weight times the temperature. So these are just different forms that you can use for the same relationship. Okay, and this ends up being very useful. So how do you use this equation? It's pretty simple. say I give you pressure is equal to 100,000 pascals, and your volume equals 1 meter. I'm picking very simple, terms. So this is 1 meter cubed. Our bar, I already told you, is 8314 joules per kilomole Kelvin. Molecular weight, I'm just going to say that's 10. Yeah. Sorry, I forgot the units of what molecular weight was. Kilograms per kilomole. And I always have to check that. You want to make sure your units are correct when you're using this. And what's left? The temperature is 300. Okay, so sorry. Let me say the temperature is not 300. That probably wouldn't balance out. But what is the temperature? That's what we're trying to find. So we say 100,000 pascals times 1. Okay, divided by let me see. Oh, I should have told you what the mass was. Let's say mass is 1 kilogram. Okay, so we divide by 1 kilogram. What else is left? We have to multiply. So multiply by the molecular weight times 10 kilograms per mole. Let me take the units out. I haven't been showing them on the rest of them. What else is left? Oh, the gas constant. So 8314. That's joules per kilomole. Damn it, I did it again. I apologize. So that'll give you what your temperature value is, which it may be fictitious, but you get the point. So, this is 1,000,000 divided by 8314. Okay, and I'll let you figure that out. And so since we kept the units at their base level, the SI units, what we'll end up getting is temperature is in degrees, or not degrees, sorry, in Kelvin. Okay, so you can just, use any other terms to find any term that you're missing. So maybe you're missing the pressure. If you have every other term, you can find out what that pressure is, or the volume. We can do the same thing. We can also do that to find out the quantity, number of moles, the mass. Maybe you even want to find out what the molecular weight is of the substance. You can still use the ideal gas law to find what that value is. So I hope this was helpful. Please let me know if you guys have any questions, and I'll be happy to help. Thanks for watching.